All right, welcome to The Explainer. Today we're diving headfirst into a seriously fascinating topic, the pure physics of motion. We're going to break down the exact, down to the millisecond science of how things actually move. We'll start with something as simple as walking down the street, and we'll scale all the way up to some of the most extreme, record-breaking speeds imaginable. It's a field of study that governs literally every single thing moving around us, and I am so pumped to unpack the whole shebang with you today. Okay. Let's kick things off with one of nature's absolute marvels, cheetahs. We all know they're the fastest land animals on Earth, but what's really mind-blowing here isn't just their top speed, it's their acceleration. They can accelerate at rates greater than 10 meters per second squared. To put that into perspective, your average high-end sports car, that accelerates at about 7.2 meters per second squared. A cheetah can go from a dead stop to 10 meters per second in just 3 strides. It's wild. And understanding exactly how we measure that massive explosion of movement, well, that is exactly what kinematics is all about.
So here is our quick roadmap for today's explainer. 1. The study of motion. 2. Scalars versus vectors. 3. Graphing acceleration. 4. The speed limiter debate. And finally, 5. The future of transit. Let's get right into it.
Section 1. The study of motion, defining the rules. It's always kind of cool how physicists can take something we do every day and boil it down to an exact, precise science. We're talking about kinematics here, which is really just a fancy word for the study of how objects move. But to track movement, you absolutely have to have a starting point, right? Think of it like your 0-meter mark. Position is simply an object's distance and direction from that reference point. And displacement? Well, that's the actual change in that position. So at its core, motion is quite literally just a change in location as measured by an observer. Think about a long jumper for a second. When they launch themselves down the track, they aren't just running and jumping. They are executing a highly complex physics equation in real time. They start at a reference point, sprint to a foul line, and jump into a sandpit. Their one and only goal is to completely maximize their displacement, to push their final position as far away from their initial position as humanly possible. They are relying on speed, strength, and technique to completely manipulate the physics of motion. All right, section 2. Scalars versus vectors, the importance of direction. Now, in the physics world, we basically measure things in 2 distinct ways. First, you have a scalar quantity. This only has magnitude or size. Distance is a perfect example of a scalar. If you run 5 kilometers on a treadmill, your distance is 5 kilometers. But hey, your actual location hasn't changed at all. A vector, on the other hand, is a game changer because it has magnitude and direction. Position and displacement are vectors. If you run 5 kilometers due north, that specific direction entirely changes the physical reality of your movement. When it comes to physics, direction is absolutely crucial. Let's put this into a super relatable context so we can see how we combine these vectors step by step. Imagine you step out your front door. Boom, that's your 0-meter reference point. For step 2, you walk 500 meters east to your school. Your displacement is now 500 meters east. In step 3, you walk another 700 meters east from the school to the library. Because you're moving in that exact same direction, you can literally just add those vectors straight together. Your total displacement from home is 1,200 meters east. Direction is the golden key that unlocks the math here. Moving on to section 3, graphing acceleration, visualizing the math. Obviously, in a physics lab, we aren't just eyeballing things to see how fast they're going. We use incredibly precise tools, like ultrasonic motion sensors. These send out invisible waves that bounce right off of a moving object, say a little motorized toy car. As that car zips in a straight line across a flat bench, the sensor feeds real-time data straight into a computer. This spits out these beautiful, perfectly precise position time, velocity time, and acceleration time graphs. It lets us perfectly capture what we call a state of uniform velocity. But motion isn't always just flat and steady, right? What happens when you introduce gravity to the mix? If you release a heavy PVC pipe down a 30-degree inclined ramp, gravity immediately takes the wheel. The pipe doesn't just move at one speed. It accelerates constantly as it rolls down. If you were to map out the acceleration time data for that pipe, it would give you a completely different graphical signature compared to the steady, predictable pace of the motorized toy car. So how do we actually read these graphs? Graphical analysis is a huge deal in physics simply because nature, sadly, doesn't come equipped with a built-in speedometer. Here is the big takeaway. If you ever want to know exactly how much an object's speed has changed over a certain amount of time, you just calculate the physical area under the line on its acceleration time graph. That area mathematically equals the exact change in velocity. It's just a wonderfully elegant piece of logic. You might be wondering, why do we even care about mapping out changing velocity and acceleration so perfectly? Well, honestly, because it's fun. Think about a classic wooden roller coaster. The entire experience, those massive stomach-dropping plunges, and that incredibly heavy feeling you get at the very bottom of a hill. That is all engineered purely by manipulating acceleration and velocity. Designers rigorously map out those exact graphs to ensure the ride is thrilling, fast, and most importantly, physically safe for the human body to handle. Up next, Section 4, the speed limiter debate, physics in society. Now let's take all this physics theory and apply it to a real-world, pretty high-stakes debate. There's been a lot of serious legislative talk regarding young drivers. The data is pretty stark. Statistics show that speeding is a factor in roughly 30% of fatal crashes, and teenagers, well, they're statistically more likely to take risks behind the wheel. So, a big question has been floated. Should governments mandate that all cars driven by teenagers have an electronic speed limiter installed, basically hard capping their absolute maximum speed at 90 kilometers per hour? Let's look at the arguments on both sides impartially here. Proponents of the idea argue that capping speed physically limits the severity of a potential crash. That's just pure kinematics at work. Plus, it significantly reduces greenhouse gas emissions because cars run way more efficiently at lower speeds. On the flip side, opponents point out a major safety flaw. A hard speed limit might actually prevent a driver from briefly accelerating to get out of the way of an impending accident. And beyond that, there's a real concern that people would just tamper with the tech anyway, basically rendering the whole law useless. And, this isn't just some theoretical talking point. This exact tech is literally out on the highways right now. In Canadian provinces like Ontario and Quebec, massive heavy transport trucks are already legally mandated to have their speeds electronically capped at 105 kilometers per hour. The entire goal there is to take what we know about mass, velocity, and momentum and apply it directly to increasing highway safety while simultaneously dropping heavy vehicle fuel consumption. Which brings us to our final stop, Section 5, the future of transit, speed versus efficiency. When we look at engineering today, there is this massive tug of war in our priorities. On one hand, you have absolute marvels of extreme speed, like the thrust supersonic car. This is an experimental vehicle strapped to 2 jet engines that hit a totally mind-boggling speed of 1,228 kilometers per hour. But the catch? It burned a jaw-dropping 55 liters of fuel for every single kilometer it traveled. Compare that to your average everyday passenger car, which sips about 0.07 liters per kilometer. We absolutely have the tech to build things that go incredibly fast, but man, the environmental penalty for that speed is just massive. And then, on the completely opposite end of the spectrum, you have something like the Midnight Sun. This is a brilliant solar-powered car designed by students over at the University of Waterloo. By completely mastering the kinematics of drag, weight distribution, and rolling resistance, this student team built a vehicle that cruised up to 117 kilometers per hour. And the kicker? It used absolutely zero fossil fuels. It is a massive triumph of engineering that prioritizes environmental efficiency without totally giving up on practical speed. Which leaves us with a really big question to chew on as we wrap up. We understand the rules of motion better today than at any point in human history. We can perfectly calculate acceleration, we can plot out velocity, and we can engineer machines that literally push the absolute boundaries of physics. But as our capabilities continue to expand, what should we, as a society, value more? Should we prioritize pushing the absolute limits of sheer, unadulterated speed, or do we prioritize pushing the limits of sustainable design to protect our planet? Kinematics gives us the math to build either one, but ultimately, society has to make the call. Thanks so much for joining me on Six Explainer, and remember to keep questioning the world moving around you.